Let R be the region in the first quadrant bounded by the graphs of x equal y to the third and x equal 4y. Which is greater, the volume of the solid generated when R is revolved around the x-axis or around the y-axis? Well, let's go ahead and draw our region R. We're in the first quadrant, so we just need to draw that. And this is expressing x as a function of y, and that's okay, but we're used to expressing it the other way for graphing purposes, and if we're revolving around each axis, we're going to need it expressed the other way as well. So if I solved these for y, this first one would be y equals x to the 1/3, and the second would be y equals 1/4 x. So we're going to need them expressed both ways, and I decided to do that because I could draw these graphs a little bit easier. I'm familiar with what the cube root of x graph looks like in the first quadrant, something like this. And this would be a line whose y-intercept is 0, whose slope is 1/4. So we'd go up 1 and over 4 and make a line. So our region would look something like this. To find our intersection point of our region, especially because I don't trust my graph paper, I'm interested in where those functions equal each other. So I'm interested in, and maybe I'll go ahead and look at them here. So I'm interested in when y to the third equals 4y. I could go ahead and move that term over and have y to the third minus 4y equals 0. Factor out a y squared minus 4 equals 0, difference of squares, and so I can see that there's intersection points on these graphs at y equals 0, -2, and 2. So the one we're obviously interested in, we've got the 0 one right here, and we're not interested down in another quadrant, so the other one would be where y equals 2. And so if y equal 2, we would have x being 8. So this would be 8 at this point of intersection, and this is where y equals 2. We could kind of confirm that by putting y equal 2 in the other one and also getting x equal 8. So this intersection point would be at the point 8, 2. Now that we have our region, we want to consider rotating about each axis. So let's go ahead and first of all rotate around the x-axis. So if we rotate this around the x-axis, we can see that I'm going to make a little representative slice here. And we can see that we would have a little thickness dx, and we would generate washers because we have the two functions, and there would be a hole in the center anywhere that this second function, the one I've got in red, the x equals 4y, was above the axis here. So we are going to integrate, and we know that's dx for our little thickness. So our limits of integration are going to be x values. We're going to go from 0 to 8 then, because that's the end of our region. And we're going to do pi multiplied by the full radius here, which would be the function value for the upper function. And we're doing this in terms of x. So let's go ahead and we'll use it like this. So this is going to be x to the 1/3 squared, that's our pi r squared, minus pi, we're going to subtract off what would form the hole in the washer, and that would be pi times the y value, which is the function value for our red graph, which is right here. So this is going to be 1/4 x squared, and then we have our dx. So there's our integral that will express the volume of the solid generated by rotating this region R around the x-axis. And let's go ahead and factor out the pi. Then we're going to integrate from 0 to 8. And it looks like we have x to the 2/3 minus, and on this the squared applies to the 1/4, so that's going to become 1/16 x squared dx. Okay, so that's going to be pi multiplied by, we can go ahead and do the integration. So 1 pi, or power, would be 5/3, but we need the reciprocal of that power out in front. And then minus 1, we got the 16th, but also 1 higher power would be a 3, so 16 times 3 is 48. So x to the third, and this would need to be evaluated from 0 to 8. Okay, so we have pi, and then we've got 3/5 and 8 to the 5/3 minus 1/48, 8 to the third, and our lower limit is 0, so minus 0. Now if we simplify that, this is a cube root of 8 is 2, to the 5th is 32, times 3 is 96. We got 96/5. Then we subtract off 8 to the third over 48, and it looks like we get 128 pi fifths. So now we want to go work the other piece of this, which is we want to rotate this region around the y-axis and see what we get for the volume of the solid generated and compare that to 128 pi fifths. So we have our same region, but we want to rotate it around the y-axis. So when we do that, our little slices are going to be horizontal slices. Envision this rotated around the y-axis. We can see it would generate kind of a bowl-shaped thing. It would actually have we have this straight line on the outside and curved on the inside. And if we were looking at these little slices, they would be washers. And if we looked at the complete diameter here, we could call that capital R. And then we have the hole in the washer right here. We can call that little r. So let's go ahead and express this volume. It's going to be the integral. Now our little thickness here is a little dy thickness. So we're going to write everything in terms of y. We're going to integrate from 0 to 2 then, looking at our y values. And we have pi. As we look at big R, it would be the x value along this red function, and x equal 4y. So the x is 4y, and we need to square that for pi r squared, minus, now we're going to subtract off the whole, so it's the circle that we would get here by doing pi little r squared, and little r would be the x value of this function, that is x equal y to the third. So this would be y to the third squared, and then we need to multiply by our little thickness dy. Let's go ahead and see what we can do to simplify this. We can factor out a pi, and we've got 0 to 2 of 16y squared minus y to the 6th, and that's dy. So now let's go ahead and do our integration. So we still have our pi, and this would be 16. We need the reciprocal of this power, so over 3. Minus, and this would be 1/7 y to the 7th, and then we need to evaluate this from 0 to 2. So that would be pi multiplied by 16/3 times 2 to the third minus 1/7 times 2 to the 7th, and our lower limit 0, so that part is 0. And when we go to simplify that, that would be 512 pi over 21. So we've got 512 pi over 21, and we could put that in a calculator to get an approximate. That's about 76.6, and that would be rotating it around the y-axis. And if we rotated it around the x-axis, we had that 128 pi fifths, and if we put that in the calculator, we can see that's a lot smaller. We've got 26.8 approximately. So answer to our question, if we rotate around the y-axis, the solid generated has a greater volume than rotated around the x-axis.